Welcome to September 3rd's LeetCode challenge, Erect the Fence. You're given an array of trees where trees at index I is the XY coordinates representing the location of the tree in the garden. You're asked to fence the entire garden using the minimum length of rope as it is expensive. The garden is wall fence only if all the trees are enclosed. Return the corners of the trees are exactly located on the fence perimeter. So we're given an array points here of trees. We have points 1, 1, which is here, 2, 2, which is here, 2, 0, which is here, 2, 4, which is here, 3, 3, which is here, and 4, 2, which is here. And it's asking you to give you the perimeter of the trees located in the perimeter of the rope, the fence. So according to the output here, so the rope would go around tree number 1, 1, 2, 0, and then it'll go to 4, 2, 3, 3, and 4 and 2, 4. Then it will loop back. So basically it loops around these 5 numbers here. Those are the parameters of the tree that will return the minimum number of fencing that it would need, minimum length of rope that it would need to fence the trees in. Similar deal here, we have basically trees at here, and we just basically all the trees will be encapsulated within the fence, all 3 of them. So there's many ways to solve this. Well, a couple of solutions. This is a hard question. There's one called the Jarvis Algorithm, another one called the gram scan, and then there's the monotone chain. I'm going to be using the monotone chain to solve it because that's one I understand the most. So here's how it kind of really works. So for instance, you have a bunch of trees spread out. When you want to do select the first point, then you basically go select this point right here, and that's good. If you go to this point, it's going to cross this point out because it knows that it's inside. It's less than the y-axis. The y-axis down here is more negative, I guess to say, for this tree. Then I'll go to the next tree, which is this one. It'll cancel this one out because it's more negative. Go to this tree, it'll keep it, and then it'll go to this tree. But this tree is more negative than this tree, but it's more to the right, so it'll cancel that out. So it's basically going to capture this point, and this point from the lower half of the hull. Then it's going to go in reverse counterclockwise direction. It's going to capture this tree, which keeps. It's going to capture this tree, which it keeps. It's going to capture this tree, which it will not delete. It won't keep because this one is more positive. It's going to capture this tree. It won't keep that because this is more positive. And then it's going to capture this tree, which it will keep. So it will go here, 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 and here, once we return the entire rope fence. So this is a quick and easy, dirty description of the monotone chain. So essentially, the idea behind the monotone chain algorithm is that it's very similar to the gram scan algorithm. Mainly it differs because the gram scan takes into consideration the polar angles of it instead. Instead of using the monotone chain, we just basically sort it and keep track of the x and y coordinates a little bit easier. So basically, we sort the points based on the x coordinate values, and if the points have the same x coordinate values, the points are then sorted by the y coordinate values. So just as we go along, and we're going to keep up track of a lower stack and an upper stack in order to go through that hull phase. In this algorithm, we consider basically a hull as comprised of 2 sub-boundaries. So it's going to be an upper hull and a lower hull, which are 2 different portions, right? We're going to go basically from left to right on the bottom hull, lower hull, then right to left on the upper hull, which is basically going to be counterclockwise. So we traverse through each of the trees in the initial 2 points temporarily. We're going to put them in a stack, and then we just consider for every point in the lower hull, if it's more right and more negative, then we're going to keep that, right? And then we're going to traverse through all the points at the bottom. So that's pretty much it. Alright, let's work this out. So the first thing we want to do is sort the trees here. So trees dot sorted, and we are given a trees are list of an integers. So what we're going to do is actually create a map of tuples, and with the tree, and we're also going to make a lambda key here, lambda key value, and that's going to be x, and that's going to be x at integer 0, and x at 0, and x at 1, which is going to be x and y respectively. We also need, for the monotone chain, we also need a function, a definition function called cross product, or cross product. If you guys are not familiar with that, I'm just going to call it cross, and that's going to take in 3 parameters, and that's going to be, so a cross product is basically finding the collinearity of the orientation of 2 points. When 3 points meet, essentially. So it's hard to describe, but the definition of cross product is as such. So you have b at index 0, so bx minus a0 times c at 1 minus a at 1 minus c at 0 minus a at 0 times b at 1 minus a at 1. So that's essentially a cross product in the simplest form. I'm not going to go too much detail about that. So next thing we're going to do is develop an edge case here. So if the length of trees is less than or equal to 3, as here, right? If there's only 3 trees, we return 3 points there because that's the number of fencing you can make around. It's just wrapping all 3 of the trees. Especially because if it's a triangle, right? You know, just wrap it all, right? If it's 2 points, if it's 1 point, just return that point. If it's 2 points, just basically return the 2 points. And if it's 3 points, return either the triangle or the line. If it's collinear, return all 3 points as seen here. Return trees. Alright, now we get into developing the lower hull and the upper hull. So as I said before, we're going to store that into a stack. And then for tree in trees, we do a while loop here. So while the length of the lower stack is greater or equal to 2, and the cross product between the lower at index 2, lower at index 1, negative 1 I should say, and tree is less than 0, we are going to pop from the lower stack, else the lower stack will be appended to the tree. So here lower is a stack, tree is a value, but also keep in mind that I'm keeping it as a tuple, so we're gonna add a tuple divider there. So next thing I'm gonna do is do upper. I keep track of the upper hull, right? So for the lower tree, we go basically from left to right, and from upper, we're just gonna go counterclockwise. So for tree in reverse tree, because we're going from right to left this time. Same deal. So while the length of upper is greater than or equal to 2, and the cross product between upper at negative 2 and upper at negative 1, and tree is less than 0, we are going to pop from the upper stack and then we are going to increment it with our tree, upper dot tree, and that's also a tuple as well, so we need a tuple divider. And we want to return the list of the set of all lower stacks that are from the beginning to the end, plus upper from beginning to the last one. Let's run the code and see. It looks the same. Okay, accepted. Awesome. So this is using the monotone chain approach, and time complexity is big O of n log n, because we're sorting the algorithm. We have a sort algorithm right here, which takes in n log n times. So further, after sorting the points, the tree is considered two cases. So it's either pushed onto the hull at the top or pushed onto the hull at the bottom. So every point is at least touched twice, either a pop function. So it's taking in a 2n big O n worst case scenario, because we are popping it, and also we do have to we add 2 here as well. Maybe better if I put. Alright, and space complexity is big O of n, because we have 1n here and then 2n here for the hull stacks. That grows up at most a size n, right? Because we do have to loop through each of the trees both times, which is unfortunate, but that's the nature of this question. So yeah, that's it. Have a great day, guys.